Hello, everyone. Happy Tuesday. I hope you had a great weekend. I went to Solstice Canyon for a hike. Also, that is the hunger walk hosted by West Food Bank. So we are working on our class project about sustainability development goals, and hunger is actually one of them, right? Yes. So that is what I did over the weekend. I hope you also enjoy the after post-election weekend. You had some rest. Turned out to be good, but we still need to put our heads down to get many things done, right? Okay. All right, and in the new week, we also have 2 new assignments. Okay, so let me show you. Share the screen. Okay. Oh, great. Okay. Okay, do you see my screen? Yes? Yes. Okay, good. So go here. That is week 10 to 11. So we are in a week 11, okay? So here, not today, this week, we wrap up this lecture number 2, analyzing patterns. Analyzing patterns. This is the number 1 fundamental thing in our advanced GIS class, okay? And today I'm going to give you a clear picture. I have my notes here, okay, to summarize, okay, how to analyze patterns, what types of patterns we are going to have, we are going to analyze, and what kind of methods you're going to use, okay? And you have a new discussion. That is discussion 11. I posted here. I posted last night. Okay, so click on it, but it's due next week. Okay, so basically this week we finished the discussion on the pattern about attributes. Okay, the pattern about attributes. Remember last week, the example I used to demonstrate the pattern is point pattern, right? We just use crime incidents. We don't care what type of crime it is, right? We just analyze the cluster based on location only, okay? But this week, we are going to analyze the patterns about attributes. Why we need that, okay? So for example, let me continue my, oh, not this one. Let me close this, okay? For example, our election data, okay? I bet the new data is coming, but this is 2016, last presidential election, the turnout data. You can see here, if you just use the location of those polygons, it's meaningless, isn't it? Because the polygon is just there, right? Oregon is always here, California is always here. There's no movement, right? There's no cluster. But in terms of attribute of the polygon, right? We have clusters. We have clusters. We have certain area, certain polygon, you have high turnout rate. Okay, for example, Colorado, these parts. We also have clusters of turnout rate, low turnout rate. For example, those southern, state and counties. Does that make sense, guys? Yes? Yun?
Yes.
Yes, okay, because you stay still. You're like, I'm still thinking.
Oh.
Okay, sorry for calling you out. Yeah, so 2 types of things you can analyze, right? Okay, but for the crime, you can see crime can happen anywhere, right? For example, those, let me turn off this one, theft, right? Can happen anywhere. The location have some meaning. They can cluster in, South Central, right? Or Long Beach or Palos Verdes. but not that many here in Santa Monica Mountains because no one live there, right? Okay, so location can also have clusters, okay? So that is two types of analysis we are going to, to perform, okay? Depends on your project questions, okay? So that is a number one. Okay, so this discussion is about attribute clusters. And today we are going to learn two new, I would say metrics, okay, measurement to measure the clusters, okay, and to evaluate how significant those clusters is, okay, those clusters are, okay. So one is called global Moran's I. That is for your global pattern, your entire study area. But from last week, you see my map, you see this map, your cluster can depend on scale, right? So when you zoom out to look at the entire Florida, you may end up with, oh, it's a clustered pattern because I see clusters here, right? Not that many here, that is a clustered pattern. You use global Moran's I to analyze it. Okay, you got clustered. But when you zoom in to those counties, since it's just so common to have those sinkholes, right? If you apply the same measurement, okay, the same global Moran's I, but within smaller area, you probably end up with, a different conclusion. No, it's random. It's not clustered, or the clusters are not significant. It depends on the scale, right? Okay, so how can you deal with such kind of situation? You just do both. Okay, when your pattern, those clustered pattern or dispersed pattern, they're mixed. When you zoom in, zoom out, the pattern can change. You do two things. You perform one, that is your global analysis to analyze global pattern, okay? And then you do another one to analyze local pattern, to identify those local significant clusters within the same, spatial extent. For example, you stay with Florida, okay? Just identify where for sure that is clusters, okay? Local clusters, okay? So that is why we have two types, local Moran's I and global Moran's I with those two metrics, okay? And you're going to answer the question in your initial post. What are they? Okay, what's the difference? And how to interpret the result. Okay, today I will give you introduction, and also from GODA, I post those two videos. Please watch, okay, and take notes, okay, to see the difference and the definition and how to interpret the result. Okay. All right, so basically summarize your learning by answering those three questions, okay? And then you're going to apply, GIS is the tool, right? It's meaningless if you never used it, okay? But since you have a very good project method, or project topics from the previous discussion, I want you to, given the project topics you chose in the previous discussion, think about how could you apply global Moran's I and local Moran's I in your project to analyze those attribute clusters, okay? For example, Jeff worked on the food access, right? The food desert. Where are the clusters of the food desert? People have low accessibility, poor accessibility to fresh grocery stores, right? So you based on counties, you can apply local Moran's I and global Moran's I, right? Okay, so think about how could you apply those two metrics to answer your question, okay? So please compose your post from those two perspectives, Okay, what are the spatial questions you plan to answer by using global Moran I and local Moran I? So if I require you to, you must use global and local Moran I. Can you give me a question? You can use those two metrics to answer. Okay, and then what are the results you expect to get? When do you interpret, and how do you interpret the result? Okay. All right, so let me pause. Any questions based on this, related to this discussion? Okay. All right, so Candice have this question. She had a, create a project about hurricane, okay? And also, Candice, could you introduce us your project idea?
Yes, I'm still working on it. I found the data set that I was struggling with for the attributes, so I should be able to start entering it now. But for South Korea, I'm trying to do the natural disasters from like 2000 to current and how it affects population, especially because population densities are different in South Korea based on topography. So that's kind of where the questions you see posted comes from.
Very good. Also, very similar to the lab one, your tapestry, the data, right? You have different attributes related to population. For example, low income, for example, poor housing conditions, right? You can totally apply global Moran I and local Moran I to analyze where are the clusters. Are those clusters on the track of the hurricanes, right? Okay, so that is the thing, the new thing you can bring in to the project here in this class, okay? All right, so that is your initial post, and then I want you to review the post of at least one of your classmates and to provide concrete suggestions, okay, to help him or her to improve the plan, okay? So basically, based on those discussions, on one thing we learn, and then we move on, in our for our project. Okay. All right. So that is the first thing you need to do from now to is due November 17th, I think. Yes, next week. Okay, next week.
Can I
Okay.
ask
Yeah, go ahead, Yun.
How big is global and how small is local? Because it sounds a little relative, so.
Very good question, Yun. Yeah, it's relative. I like that word, relative. So if you think global is the entire Earth, right? Then local will be different countries. Like globally, you will have the pattern related, maybe coronavirus, right? COVID-19. And clusters maybe, well, at the beginning of this year, that is in Asia, China especially, but now it's in Americas, right? That is a local pattern. But if you just focus on, your entire United States is your global pattern, right? Then each county will be clusters. So you will see, oh, at the beginning, that is New York, okay? Then southern part of this country, that is your local pattern. Now in the Midwest, right? Okay.
So it depends. So it depends on like scope of your
exactly
project. Okay.
Exactly.
Thank you.
The spatial scope. I like that, Professor Yun. The spatial scope. So you set up your study area. That is your global. Okay, don't be fooled by global. You don't have to, just use the entire globe, the entire Earth, right? So when you set up your study area, the entire study area will be your global pattern, but within your study area, okay, within your study area, those clusters will be local pattern. Does that make sense? That's totally relative, depends on your study area. Okay,
Yeah.
I like that because you're going to have the question about this in your quiz. Okay, all right. And then that is our new lab, okay? So the new lab, nothing new. Where's lab? Here. Okay, so basically the lab is about point pattern. It's just a location, okay? So you have two options. You have ArcGIS, because I don't want you to miss the opportunity advantages of ArcGIS and how beautiful the maps are, okay? And the advances, the new advances in ArcGIS. So if you can access ArcGIS, you're going to follow the instructions here, and you're going to create a new story map or an information board, okay? Information board for your crime statistics meeting, okay, for this county, okay? So don't be scared by, oh, that's so complicated. No, not at all. If you follow the instructions, it's actually very easy. Okay, so it's very, very useful. Think about next time when you are hired by LAPD, for example, right? You can use exactly the same method to analyze the crime pattern in LA. Okay, or do a similar project related to LA, the crime. Okay, but if you cannot, okay, access ArcGIS, you have a Mac or the Citrix totally, doesn't work for you, you can use, or if you just want to try, go ahead to follow QGIS. You just need to finish one, okay? QGIS have this hotspot analysis. This is also a lab, okay, instructions. And you can see the method we are going to use actually is kernel density. Where is the kernel density? Crime kernel density. Control F, kernel. Yes, so you're going to use kernel density we focused on last week, okay, to create this map. And also this instruction also give you the many details, how to make a map and how to, change the symbology with QGIS. Okay, I think it's a very good practice. You definitely welcome to finish too. Okay. All right. And then for QGIS, okay, for QGIS, if you don't know, okay, the heat maps in QGIS3, here is a video you can watch how to do that. Okay, you don't want to read, just watch here. Okay, and here I ask you to submit a static map. If you don't know how to create a static map, just a layout, go ahead to watch this video. Okay, go ahead, watch this video. All right, so this lab give you the practice on ArcPro and QGIS. On Thursday, I'm going to demonstrate another one, GODA. Okay, GODA. So in the whole week, you will learn three things, three ways, three software you can perform the hotspot analysis based on location and also based on attributes. Okay, all right, and you're welcome to use any of these in your project. Okay, okay, so just want to give you as much as I can. Okay. All right, so any questions? Okay, wonderful, sounds wonderful. Okay, so this one is also due November 17th. So you have the full week, okay, to focus on those two, okay? Okay, all right. Okay, then let me stop share, okay? So today our meeting is a little bit theoretical, okay? I know some of you don't enjoy theoretical things. I will be like, professor, very old-fashioned professor, just go over the slides. So I want to give you some fun, okay? I asked your classmate, James, to share with us his map finished in GIS20 class, which is amazing. Okay, mapping always make me happy. I believe it also can make you happy. So floor is yours, James. Go ahead.
All right, great. Let's see if I can pull it up here. You guys see the screen?
Yes.
Okay, great. Yeah, so what I wanted to look at was how people moved, or actually, in fact, didn't move throughout Harris County, Texas after Hurricane Harvey in August through September of 2017. So what I wanted to take a look at was the places that are in a flood zone, either 100-year or 500-year flood zone in Harris County, and whether people stayed in those flood zones during the year afterwards, over the course of 2018, which would be the full calendar year. And so what I did was I took polygon layers for 100-year and 500-year flood zone in Harris County. I put those together. I basically I joined them, I guess. And then I clipped the census tracts with using that flood zone to find all of the areas and to basically break up the flood zones by census tract, so I would have access to the data, particularly geographic mobility data. And the statistic that I wanted to look at the most was here, this percentage of population that remained in the flood zone in the year after the hurricane. And then I just broke that up into 5 groups. There's an equal distribution in each group. And then what I wanted to see was my hypothesis about why people stayed in these flood zones. And my original hypothesis would be that if you're low income, you would have less ability to move. It wouldn't be so easy for you to move the year after, and that you're often restricted to housing tracts that are high risk. Those tend to be the places that have, cheaper apartments. These are the places that are in flood zones generally. But as you can kind of see, I marked all the census tracts that are quote unquote low income, which are below the median household income for the county. I marked those with these hatched symbology. I also kind of highlighted them with the blue. But you can see that my hypothesis is quite wrong, not without any statistical kind of verification, but just kind of like as a black swan. You can see that the places that people move the most are in fact usually the lower income, and the places where people remained, like this one here, are not low income at all. So then I had to kind of reassess what I think is going on here. And when I looked at 2 case studies, one of which is the highest percentage of people remain over here, tract 3402, and the lowest, tract 2309. And what you can see is the household income for the places where people stayed the most, just as a case study, is much, much higher than the place where the most people left. So now my question is, why? Why would this be the case? And the things that I want to look at now, moving forward, are how many people own houses and how many people rent in each of these census tracts. Because if you have a house, much harder for you to get up and leave. Whether if you're low income, you may in fact be a renter, either easier for you to, let's say, jump from this place in a flood zone to maybe just somewhere else of similar value, but outside the flood zone in the year after. Much easier for you. Or there's actually rivers kind of like down in here, rivers, lakes, etc. These might be high value properties, and you may be less likely to give up a nice house that you have like lakeside, riverside, and that may encourage some people to stay even despite the floods. You may say, I've invested a lot in this property. So for the future, I kind of want to make 2 more maps, one of the same thing, essentially, how people moved, but track it against housing price or like house value, and also track it against percentage of, or like a net difference, owners versus renters for each census tract. So that in essence is my map. Yeah, if you have any questions.
Guys, any questions for James?
How did you determine like what percentage of residents remained before versus after Hurricane Harvey?
Yeah, they have on the American Community Survey. I actually got it sent to my house this year. They have a question that is, it's basically, it's not a question, but they use the data to figure out whether you were in the same location 1 year ago at the time of the survey. And they upload that to the census.data.gov website. And I just took that data for the people who remained in the place, divide by the population to get my own statistic. It's not actually a perfect statistic, but it's pretty close to what I'm looking for. I can't remember exactly what's wrong with it, but it's not perfectly the number of people that remained. It's closer to like the percentage of people that lived in the same location 1 year ago. So it's not quite a measure of staying versus leaving, but very close.
Thank you for the question, Hunter. And thank you for answering it, James. Here's another one for you from Candice. Okay, James, you might also want to look at renters that were forced to move due to structural damage that the landlord couldn't or wouldn't fix. That would force a change in location as well.
That's possible, actually. They have data sets because of the hurricane that basically are count of different levels of damage in each census tract based off. Yeah, so you can look at these and assess the level of damage of basically each building, and I would say that's plausible. That's a good. I don't know how to do it at scale, but it is a good question to look at. Maybe to focus on certain tracks as case studies first.
That's wonderful. Great answer. Okay, sorry, I have to mute myself because I hear an Amber Alert or something. Something happened. Okay, so let's zoom out. Okay, I mean, let's look at the entire picture. Okay, so you can see what James did here actually answered 2 general questions. So first, he wanted to find out where are the movement due to Hurricane Harvey, right? And your brilliant human brain, right? Very good at identifying the patterns. And you can see if you just focus on, those percentage of population that remained in flooding zone by tract, you will see a lot of clusters, right? And that is the clusters based on what? Based on attributes. So you can see I can identify here. Okay, maybe here. Okay, maybe here. Okay, I don't know other things, but maybe here. I say this, right? Okay, and the number 2 types of the question is, okay, why? See, naturally, you're curious about those 2 things, patterns, clusters especially, and also what other factors create those patterns, right? Okay, so that is your spatial thinking. Don't think it's hard. That is in your blood. That is our new natural curiosity. Okay, so you can see, well, I can identify it. But if Yun challenged me in my, defense of my thesis, Yun said, Jing, then how sure you are? I don't see those clusters, right? Candy said, good job, James. Yes, yes, indeed. Yeah, so how sure you are? I don't see. I also see here maybe another cluster, right? Okay, how do you define? Maybe Hunter will challenge me. Jing, how you define clusters? Based on what you claim that it's a cluster, right? Okay, so that is where, okay, the point you need those quantitative spatial analysis method to help you out. Okay, this is based on this measurement, maybe Moran's I, maybe kernel density or k-means or whatever we learned in the class, right? That is how I identify those clusters. And here is how significant they are. Okay, later we will see that. What do you mean by significant? Okay, and let me annotate, okay, to give you a full picture. So the number one in most of your spatial analysis case study is you want to first identify spatial patterns, right? And then, you measure how significant it is and significance. Okay. And number two thing you want to ask, why? Okay. What are the factors or how the patterns relate to other things, right? So that is a spatial relationship. So you can see we focus on this one this week, in the past 2 weeks, actually, identify patterns. Okay, next week, week 12, we are going to analyze this. Okay, the relationship between different attributes, basically different layers. Now we just based on one layer. Okay, does that make sense? Yes? Okay, give you a full picture. Okay, so don't get lost in this forest. We want to see the entire picture like remote sensing. We see from the top. Okay, all right, so James, you can stop sharing and let me share. Okay, thank you. Okay, so let's see. Let's share the screen. Okay. All right, so let me go to my slides. Okay, so here, very simple, actually very straightforward. We have 3 types of patterns. Okay, there's the study video number 1. You can see, the real world example. But 3 types: random, clustered, and dispersed. Okay, well, in most cases, we are more interested in clusters, right? When people or phenomena, they gather together, okay, they form some clusters, okay? We want to understand why, what contribute to it, right? Okay, so dispersed pattern in our, nature is a little bit rare, relatively rare, okay, relatively rare. So the best example I can think of is our mountain lions, okay, because they just want to claim their territory, try to stay away from each other. So you will have, their habitat, the mountain lions, you may have this dispersed pattern. Okay, so basically opposite of your clusters. Different events try to stay far away from each other. Okay, far away from each other. But in most cases, we focus on clusters. Okay, so you can see, well, then those are the definitions. Okay, so clusters basically is objects with similar attributes, okay? Similar attribute values tend to be close to each other, or they just geographic location close to each other, okay? Disperse, just the opposite, okay? This is the definition. But when you try to identify those patterns, how can you do that, right? How can you claim, okay, this is the clusters and that one is not cluster, okay? You may think, okay, we can just identify that, eyeball that. Well, I say this one for sure is cluster. Maybe 90% of people will agree with me, okay? But if I say this one is also cluster, maybe, you know, just 50% of people will agree with me. People will say, no, yeah, that's not that clustered, right? Okay, so then you can see what is the basic idea. We compare to this random pattern, right? Okay, we compare, we just assume there's a theoretical, you know, random pattern, like you throw a bunch of, you know, card, you know, your poker card, okay, onto the floor. That's a random pattern, as opposed to you on purpose organize them, you know, one card next to each other, right? Next to the next one. Okay, so you compare to the theoretical random pattern. I see a chat box. Okay, Candy said, I want to make sure I understand this correctly. The attributes could be crime in general, but then it can also be subsets like disabled vets or PPL who donate, like we saw this weekend. Yes, yes, exactly. Okay, two types, attributes and location. Okay, yes, but no matter how, okay, attributes or location, we need to identify the pattern by following this template. Okay, so first you visualize the data. You just you know, map them out, pull them in to your map, okay, to your ArcGIS or QGIS or GeoDA. Okay, and then use a statistic measurement matrix, okay, to measure the degree to which features or values are clustered, dispersed, or random by comparing the random pattern, okay, the random pattern, the pattern for different sets of features over time, okay. So basic idea, you compare the things you mapped out. Let me move. Okay, you compare the actual distribution of the features, also known as observed distribution. So basically that's the thing, you just pull into your map with a hypothetical random distribution pattern, okay, of the same number of features. Say you have 100 here. When you generate the random pattern, you also need to use 100 objects, okay, of the same number of features of the same area, your study area, your global pattern. Okay, so this is also known as null hypothesis. Null hypothesis. Okay, all right. So just you know, hypothesis is this random, and we want to compare our actual pattern to this random, and to see how significant they are different from each other. Does that make sense? Okay, I hope. Okay, so for example, you say Jing is you know, Jing is short. Okay, this short is you know, a very subjective thing, right? You probably compare to something to say Jing is short, and Jim is tall. Okay, because his height is above average. Okay, Michael Phelps, he swims fast, right? Compared to average speed. Jing is slow compared to average speed. We always compare. Same thing here. Okay, so here, then Vangelis have this question: how do we generate random pattern? Very good question, Vangelis. Very good. Okay, hypothesis. So you will have like, you know, student distribution, or it's called what, the croissant distribution. It's always remind me the pastry from France, croissant distribution. And also we have those theoretical statistics theories to define those theoretical random pattern. Okay, but you don't have to worry about it. I just want you to get this basic idea where that significance come from. Okay, and how can you, you know, claim this is a clustered pattern. Okay, yeah, or we have Gaussian distribution, you know, T student distribution, different theoretical distribution. Okay, all right, then let's see. Candy said, how do we know when we want to use one layer for attribute like the crimes one, or multiple layers like election of this weekend? How do we determine the number of layers? Oh, Candice, now I see your confusion. In this week for the clusters, we just focus on one layer. Okay, we use one layer. For example, in terms of turnout, you have your clusters, right? In terms of poverty, you have another layer of clusters. Okay, you can use multiple attributes, but it's more complicated. But here, let's focus on one attribute at a time. Does that make sense? Yes?
Yes, thank you.
Okay, all right, good. Okay, then you can see we have two things to measure, right? How different they are. Okay, I want it as different as possible. Then I will be more confident to claim it's a clustered pattern. Okay, let me repeat. You want to measure two things: how far this distance is, right? The further they are, the more confident I am, right? As in my analysis. Okay, so that is your two things: your z-score and your p-value. Okay, your z-score and your p-value. So basically your z-score will measure this distance, how far I am from this random. Okay, so when you see in your result, the z-score is large. Okay, that means, oh, they're very different from your random pattern. Okay, and p-value indicate how likely you made a mistake. Okay, how likely you made a mistake. Okay, you claim, okay, they are very significant from each other. Basically, that's your confidence level or your significant level. Bottom line is, you want your z-score is very large, but your p-value is very small. You know that, right? Okay, you know that. Okay. All right, any questions by far? Okay, general yes.
Is a z-score like the alpha value?
What's that?
Is the z-score like the alpha value?
Alpha value is based on, I think it's a T statistics, right? Something.
Okay.
Yes, so you don't see alpha here. That's a different statistics.
Okay.
Okay. All right.
Jing,
Okay. Yeah.
Jing, when you measure against the random distribution, how are you generating like a random distribution over the space?
Based
And
on
how, and
skill.
is it just one, or do you like generate like 1,000 and test it
Exactly.
against all of them?
I like your question. So you can see here, you need to use the same number of features. Say in LA County, in the past week, I have 1,000 crime incidents. Okay, I want to analyze what kind of pattern it is. Then in my hypothetical random pattern, I need to use the same number, 1,000 random points. Okay, I just randomly distribute all these points over LA County, same area. Okay, so you can see here the thing. When you create those random pattern, you have, many options, right? Every time you generate this random pattern, you probably have different thing, right? So you want to repeat this process many times. So that is why when you use GODA, when you use ArcPro, when you use QGIS, you will have the option how many times you want to repeat. Okay, numerate, right? Yes. Very good question. Now we are touching the core. Very good. Thank you guys for the question. Okay, let me pause. Let me share with you this very interesting video to highlight what is p-value and how you understand it and why we need it. Okay, clear the drawings. So I think it's here. Okay. By the way, this channel you can subscribe. It's very interesting.
Values, yeah. StatQuest.
Oh, let me start from beginning.
Gonna talk about p-values, yeah. StatQuest. Hello, I'm Josh Starman.
Oh.
Welcome to StatQuest. Today we're going to talk about what p-values are and how to interpret them. Imagine I have two drugs, drug A and drug B. And I want to know if drug A is different from drug B. So I give one person drug A, and I give one other person drug B. The one person using drug A is cured. Hooray! The one person using drug B is not cured. Bummer. Can we conclude that drug A is better than drug B?
Let me pause. Can we?
I don't know. Is drug B a
technically, no.
placebo?
Right, exactly. Like the new vaccine, right? Okay, let's continue.
Nope. Drug B may have failed for a lot of different reasons. Maybe this guy is taking a medication that has a bad interaction with drug B. Or maybe this guy has a rare allergy to drug B. Or maybe this guy didn't take drug B properly and missed a dose. Or maybe drug A doesn't actually work, and the placebo effect deserves the credit. There are a lot of weird, random things that can happen when doing a test. And this means that we need to try each drug on more than just one person each. So we redo the experiment, but this time we give each drug to two different people. This time, both people taking drug A are cured. Hooray! And one person taking drug B is cured and one person is not cured. Hooray! And bummer. Is drug A better? Are both drugs...
Sorry. Is drug A better or both? Bummer. How about this time? I tried
We
two
have
things.
this. We have the same problem on drug B that we had in the first test because we don't know if someone, like, maybe took it wrong or they aren't interacting with it well.
There's not enough.
Yeah, I don't think we have enough
Yeah, we need a
numbers
bigger
to
sample
say.
size.
for my students. Let's continue. You totally got it. Okay.
The same? We can't answer either of those questions because maybe something weird happened to this guy that caused drug B to fail. Or maybe something weird happened to this guy, like maybe the drug was mislabeled and he actually took drug A, and that's why he was cured. So now we test the drugs on a lot of different people. And these are the results. Drug A.
How about now, guys? You see the result.
Yeah.
Yeah. And Lenore said, yes, definitely.
Yeah, we see
A
the
is
results,
better.
so we can definitely say A is better now.
Okay. Any different opinions?
I think they need to give 1,432 people drug A.
Yeah, it makes sense.
Not exactly same, right? Okay, then how about, okay, this just, I say no, because those people, they're healthy. Okay, they're, physically, better, in better conditions than group B.
I don't know if that could be, you could get like exactly this number and say that's true for everyone.
Maybe just 1,000 athletes or something.
Oh, that's, you'd have to have a similar sample pool for
Yes,
both of the
control.
drugs then.
That's exactly right. That is exactly why when we compare clusters to random, you need to use the same number, like question James asked, okay? You need to do that over the same area. Okay, make sure your comparison is fair. Make sense, guys?
Yes.
Yes, thank you. Okay, so let's continue.
A cured a whole lot of people, 1,043, compared to the number of people it didn't cure, 3. In other words, 99.7% of the 1,046 people using drug A were cured. In contrast, drug B only cured a few people, 2, compared to the number of people it didn't cure, 1,432. In other words, only 0.001% of the 1,434 people using drug B were cured. If these were the results, then it would be pretty obvious that drug A was better than drug B. In other words, it would seem unrealistic to suppose that these results were just random chance and that there is no real difference between drug A and drug B. It's possible that some of these people were cured by placebo, and some of these people were not cured because of some rare allergy. But there are just too many people cured by drug A and too few cured by drug B for us to seriously think that these results are just random and that drug A is no better or worse than drug B. In contrast, what if these were the results? Now, only 37% of the people that took drug A were cured, compared to 29% that took drug B. So drug A cured a larger percentage of people. But given that no study is perfect and there are always a few random things that happen, how confident can we be that drug A is superior? That's where the p-value comes in. P-values are numbers between 0 and 1 that, in this example, quantify how confident we should be that drug A is different from drug B. The closer a p-value is to 0, the more confidence we have that drug A and drug B are different.
Okay, guys, I hope to this point it makes sense. Okay, so the number here, maybe that is your z-score. You can see, oh, based on z-score, I can see my drug A or your pattern is more different from random. Okay, but how confident you are, right? Then that is the p-value comes in. Okay. All right, let's continue.
So the question is, how small does a p-value have to be before we are sufficiently confident that drug A is different from drug B? In other words, what threshold can we use to make a good decision? In practice, a commonly used threshold is 0.05. It means that if there is no difference between drug A and drug B, and if we did this exact same experiment a bunch of times, then only 5% of those experiments would result in the wrong decision. Yes, this is an awkward sentence. So let's go through an example and work this out, one step at a time. Imagine I gave the same drug, drug A, to two different groups. Now, any differences in the results are 100% attributable to weird random things, like a rare allergy in one person or a strong placebo effect in another. In this case, the p-value would be 0.9, which is way larger than 0.05. Thus, we would say that we fail to see a difference between the two groups. If we repeated this same experiment a lot of times, most of the time we would get similarly large p-values. However, every once in a while, all of the people with rare allergies might end up in the group on the left, and all of the people with the strong placebo reactions might end up in the group on the right. As a result, the p-value for this specific run of the experiment is 0.01, since the results are pretty different. Thus, in this case, we would say that the two groups are different, even though they both took the same drug. Oh no, it's the dreaded terminology alert. Getting a small p-value when there is no difference is called a false positive. A 0.05 threshold for p-values means that 5% of the experiments, where the only differences come from weird random things, will generate a p-value smaller than 0.05. In other words, if there is no difference between drug A and drug B, 5% of the time we do the experiment, we will get a p-value less than 0.05, aka a false positive. Note, if it is extremely important that we are correct when we say the drugs are different, then we can use a smaller threshold, like 0.00001. Using a threshold of 0.00001 means we would only get a false positive once every 100,000 experiments. Likewise, if it's not that important, for example, if we're trying to decide if the ice cream truck will arrive on time, then we can use a larger threshold, like 0.2. Using a threshold of 0.2 means we are willing to get a false positive 2 times out of 10. That said, the most common threshold is 0.05 because trying to reduce the number of false positives below 5% often costs more than it's worth. So, if we calculate a p-value for this experiment, and the p-value is less than 0.05, then we will decide that drug A is different from drug B. That said, the p-value is actually 0.24, so we are not confident that drug A is different from drug B.
Okay, so let me stop here. Okay, so you can see here we covered one very important concept. It's a false positive. You know, every time we compare to the random pattern, right, we still could make mistake, right? Okay, so p-value also measure when you have this threshold. You compare to this threshold. Okay, how likely our claim, our conclusion is a mistake. Okay, so if that, you know, is not significant, you know, like how sure you are the ice cream truck will arrive on time, you can have a higher threshold. okay, like 0.2. But if for our vaccine, COVID-19 vaccine, the threshold, you may want to claim that as, 0.01 or 0.001, because it's important to, unlikely to have a false positive, right? So that is your threshold come in, okay? Usually we will just use, 5% or 0.05 as our threshold. As long as your calculated p-value smaller than that one, you can say you're confident. Okay? As long as it's smaller than 0.5, you can say you are confident. Make sense, guys? Okay, so that is your significant level. Okay, so this one is, it's just a threshold. So let me stop here.
So how did you decide where your threshold is? Is it just experiment per
Before we're
experiment?
done,
Sorry. Say that again, sorry.
So how do you decide, I guess, where your p-value is? Is it just experiment per experiment?
No, your threshold depends on your question. Okay, usually we'll just 0.5%, but your p-value is calculated. It's every time you compare to the random pattern, you will generate a z-score and p-value, and then you basically average them out. You don't have to know the process to do the calculation, because software can do that for you. You don't have to worry. I won't ask you to do, calculate by hand. But
for the threshold, like, is it like, are we supposed to know, like, it should be more or less this amount for this type of work, or?
Right, so that is, you want to use this default one, 0.5. But if you want to use a more strict value threshold, you will use 1%. But for most our project, we just choose, 0.05.
Okay.
Okay, yeah, so that is a subjective, the choice, the threshold. But the real p-value you calculate using ArcGIS or QGIS or GODA, that one, you have that in your result. And your job is to interpret that value. Your job is not to calculate it. Bless you.
Oh, thank you.
Okay, so let me see the chat box. Okay, so our p-value is evaluated with a random so that we can show our confidence value. Exactly, Candice, you got it. Yay, hooray. Okay, so
I'm taking social stats for graduation this semester too. So we just talked about that 2 weeks ago.
That's great.
But we have to hand calculate it. So I was like, wait, what?
Then you will be the master of p-value. So guys, from now on, ask Candice about p-value, okay? All right, okay. So let's go. Let me share again, okay? Then when we have this question solved, actually the Moran's I and other things will be very easy, okay? So we can relax. So let me share. Okay, so let me close this. All right, okay, so we finished this already. Let's see. Let me move our chat. Okay, so we finish this global pattern. Okay, and last time we basically finished our density-based clusters. That's just on location. Okay, and distance-based. Okay, we finished them. And here, that is our attributes. Okay, our attributes have the similar thing, cluster or random. Okay, so but we don't call them cluster or random, but same idea. Okay, so if you see the clusters, we actually call them positive spatial autocorrelation, because like Candy's question, we just focused on one attribute. we don't, consider other attribute, how they related. That will be next week. The relationship, the attribute relationship. Okay, just one attribute. So we call that autocorrelation. They relate to themselves in terms of the same attributes, but in different polygons. Okay, so you can see this will be, clustered things next to each other. Since it's tracked next to each other, they have the same or similar values, right? As opposed to this negative spatial correlation. So you can see that's, equivalent to our discrete, okay, dispersed pattern, okay, in terms of location. So you can see the polygons next to each other, they tend to be different, like your chessboard, right? Okay, then your zero will be this random pattern, basically. So when you do the, spatial autocorrelation, you actually compare this with this, okay, or this with this, and to see how significant they're different from each other. Okay, does it make sense? All right, then different, the Merriman, okay, like Moran's I, the Lisa, or Gary C, that is just different, calculation, different equation, but the basic idea is here. Okay, so here you want to know what is positive, what is negative, and what is random. Okay. All right. Okay, so let me clear my drawings. Okay, then first, don't forget we have global pattern based on your entire study area, okay, and local pattern. So for our measurement, let's just focus on Moran's I, because Gary C just the similar idea, okay? So here you can see, oh, here, okay? Gary C and Moran's I, for locally, you don't have a map, okay? You don't, in your result, you don't have a map. You just have this result, okay? This, this result. It's like a report, okay? In this report, you will have, for example, your global Moran's I, have this number, okay? And then this is your randomness, okay? And you can see this is your z-score. This is your p-value. Okay, when your z-score is very large and when your p-value is very small, that means I'm very, very confident it's a clustered pattern. Okay, make sense? Makes sense. Okay, all right. You can see the difference, the only difference between Gary C and Moran's I is this one. Gary C used the difference between any two adjacent features, adjacent polygons. I calculate the difference between neighbors. But Moran's I, we compare each polygon with the global mean. Okay, global average, your entire study area, the average. That's the difference. Okay, but you won't have this, you won't have any maps. You only have a report. Okay, because that is the evaluation for the entire study area. Okay.
So the global Moran works more off of like the what do you call it, standard deviations, and then gives you the z-score?
Yes, well, that is the evaluation for the entire study area. How about I demonstrate how to do that in ArcPro. Okay. Let me use my mouse. Okay, so say here, do you see my map, my ArcPro? Okay, so let's do this for, use our turnout. Okay, so here, let's search tools. Okay, and here you can search Moran's I, right? So you can see you will have two, global and local. Global and local. Ansel Lin is actually the creator of GODA. Is a professor, okay? All right, so let's do global Moran I. So you can see my input features will be county election 2016, okay? County election 2016. Let's just use this one, okay? And your field will be what? Turnout, voter turnout, okay? So I want to report, okay? Otherwise, we'll just be in your, processing the result, okay? You won't see any report, okay? And here, well, here is a very important thing. How you define neighbors, okay? Based on what? Based on what? You can use different methods, okay? How do you, claim there's a, they're close to each other or they're far away from each other? You need to calculate distance, right? Okay, I just use, those default settings, okay? Let's hit run, see what we get. See, now we don't have any spatial layers, right? So, oh, hold on, environment, okay? Coordinate system, we want to use, I think it's this one. Oh, no, let's see, this one. Yes, we want to use a project PCS because we're going to calculate the distance, okay? And yeah, okay. All right, let's hit run.
Is square distance part of a spatial relationship method?
It's based on your, the distance to measure how close they are.
Okay, and I guess, I mean, it does it by itself, right? Like you don't calculate it yourself.
No, you don't calculate yourself. Yes. So yeah, so basically when you say, when the similar values, they're close to each other, you can see this closeness is also, you need some measurement, right? Here in this global Moran I, we use inverse the distance. Okay, yeah. All right, so you can see there's nothing, no maps, right? No maps. Okay, then you can click on this view details and you will see this report. Okay, here we go, report file, where it is. Okay, so you can see here, I chose to, generate this report. So this is HTML file. Okay, you can click on this one. You can see, wow, our turnout is very significant as clusters. Right, their cluster pattern. Why I say that? Because my Moran I is this, that's the measurement. Okay, by the way, the global Moran I, if it's positive, that means positive spatial autocorrelation. Okay, if it's negative, it's negative. Okay, and then you can see my z-score is very large and my p-value is very small. Okay, so that is why. Yeah, go ahead, Candice.
Would it be safe to would it be safe to say if the Moran is positive, then it would be clustered, but if it was negative, it would be dispersed?
Totally.
Okay.
Yes. Okay. So here the sign here also indicate is positive or negative. But if you're closer to 0, then that's not, very significant to your random. Random is 0. Okay. And then you can see it's handy. You can just, copy and paste this result. You can right click on that, save the image as, and include this image, this report in your final result, right? To help people understand your analysis. But you can see here, I know for the entire, let's go back to our map. For our entire, lower 48, the state, this is a clustered pattern, right? But we don't know where are the clusters. The method didn't give me the result, right? Okay, then that is the point we want to use Moran's I, this local Moran's I. Okay, so let me first show you how to do that since we're here. So same cluster, same input layer, okay, same input field turnout, and then you can see now I need to identify where I want to save this output feature class, which is a map, a spatial layer. Okay, so you can see I save that in my GDB, okay, and we call that county election, you know, the cluster outliers. Okay, and then same relationship. Okay, and then here I just use, you can see here, number of permutations. That is how many times you run this. That is a James question, right? Every time we compare to random, how many times we should repeat. Okay, this time we choose 500. Okay, and then let's hit run. Okay, here we go, guys. Chairs. Okay, let me move that over. Okay, so let me close this. Oh, I probably forgot to okay set up the distance, but it's, let me do that again. Okay, so I should use this. Okay. Okay, number 2. Run. All right. Okay, so you can see when you use different different coordinates, you actually have different result, but very small difference. Okay. All right, so you can see this time you don't have the report. Okay, I didn't, you know, set up the report, but you do end up with a map. Okay, when you have a map, let me remove this one. Let me turn off this one. When you have a map, you can see this local Moran's I actually have these. You have 4 or 5 categories, right? Okay, let me annotate here. You have high cluster. You have low cluster. You also have high-low outlier. You also have low-high outlier. This is what you get from local Moran's I. Okay, it not only can identify the clusters, okay, but also high value, high turnout cluster or low turnout cluster. Okay, and also this local Moran's I can also give you this outlier. So compared to my neighbors, okay, you can see those high-low cluster. That is, my county have a high turnout, but my surrounding counties have a low turnout. Okay, as opposed to this low-high outlier, that is you compare to your neighbors. Yourself is a low turnout, but your surrounding area is high turnout. This is more meaningful when you maybe apply, when you analyze, you know, the like COVID-19, right? For example, LA County, we have a high infection rate, okay? But our neighboring counties have a very low infection rate. Okay, so well, then we probably need to focus on the control, the, you know, stay in shelter, the order. Just focus on LA County, right? Not the surrounding counties. But what if, for example, Orange County, okay, have very low infection rate, okay, outlier compared to the surrounding neighborhood, you have a high infection rate. Then Orange County will be a low outlier, right? And then you need to protect yourself. Don't allow people to travel. Does that make sense, guys? How to interpret the result? Okay, but for the wide area, it just, you know, not significant. Okay. For ACT-PRO, they also give you this histogram. Okay, you can double click on it or click on it, okay, actually, to see the histogram of turnout, to see whether it's a Bell Gaussian distribution. Okay, but more interestingly, you can see this one. Let's open it. Okay. All right. So you have this scatter plot. Okay. So you can see, well, here you have 2 dimensions. Okay. You have high, you have this low, this should be spatial lag, that is the distance. Okay. So you can see you're close to each other, but you're very not that you're close to each other, but you are not, let's see, low, high outlier. I'm a little bit confused. So this spatial lag basically is the distance. Let's see, and your local turnout. Okay, how to phrase this? Basically, those are, you know, those counties, by the way, you can select them. You can select here, okay? Those counties are those counties you have high-low result. So basically, yourself is high. Yourself is high, but your surrounding is low. Okay, but you can see if I just select this quarter, okay, this you know, this part of the plot, I have those red area for sure, but you also have those you know, white area. Means itself it's very high value. It's different. It's higher than the surrounding area, but not significant. Okay. Well, let me think of a better interpretation. Okay, I blank out at this point. Let me share with you next time. Okay, I don't want to confuse you if I come use a bad example. Okay, so here let's go back. Clear the drawings. All right. Okay, then you can see what we just did. The local Moran's I actually is this one. Okay, so you can see you compare each of them with the mean. Okay, with the mean based on your definition of the local, the neighborhood. Okay, that is the inverse distance, our area. Okay, our local area. All right, so chat. Candy said, is high, low like where you are in a city? There is a lot of lights, but as you leave the city, there is less lights. Yeah, you can say that way. Okay, and you can see this is your local Moran's I. Okay, local Moran's I is able to identify outliers as well, not just the clusters. Okay, not just clusters. That is the one advantage of your local Moran's I. Okay, but you can also do this one. Okay, this is a local Moran's I. Here, you also have this local GI star. Okay, this one in ArcGIS, we also called it. Let me clear my. Selection. Okay, let me turn off this. Okay, let me turn off this. your local, your GI star. This is another one, okay? They're similar. It's called GI. Okay, so you can see you have this global GI star. You also have this hotspot analysis. GIS odd GI star. Okay, don't be fooled. They do the same thing, but they don't give you the outliers. That is the only difference, guys. Don't be overwhelmed by the name. Okay, compared to local Moran I. So local Moran I, you can see you have high, high, low, low, right? Those clusters, but you can also have the outliers. That's why it's called, you know, cluster and outlier analysis. But GI star, that is just the hotspots. Okay, so let's see what we have. This one, same thing. Input field, turnout, okay, hotspots. Okay, you can, you know, use different method to define neighborhood, okay, to compare to the mean, right? Okay, so I don't want to use this. And environment, let's change that to this Alberts. Okay, same as input. Okay. Okay, all right. Okay, so run. All right. Okay, so you can see this one give you a different map, right? Okay, let me close this. Okay, this one give you a different map. This is generated by your hotspot analysis, your GIS odd GI star. Okay, so you can see you just have two types, but this one give you significant level. Okay, and you will have hotspots. You will have very significant hotspots. Moran I doesn't give you this. Okay, and you have 95, you have 90 hotspots, and you have cold spots. Okay, low turnout. So if you want to highlight those cold spots, you may want to, you know, change that to another very significant, you know, darker blue or something. Let me change that darker, like this. Okay, so you can see those are the significant cold spots, 99%. All right, okay, so that is the only difference. So you can see actually it's very simple. Okay, when you understand local and global pattern, right? Okay, so this global GIS thing, basically it's similar as global Moran I, just give you a report for the global pattern, the entire study area. Okay, and then when you do this, when you finish this, if it's clustered, it's very meaningful to go ahead, okay, go ahead to use those local Moran I or local GIS GI star to identify where are the clusters, okay, because for certain area, it probably is random, right, to identify the clusters. Okay, that's it, guys. That's it. That's it. So today we basically finished the theoretical thing, okay, and also show you how to use it, how to analyze this with ArcGIS, ArcPro. Okay, so here, okay, we start from here, different pattern, and make sure you understand the basic idea how to, you know, claim it's a clustered pattern. We compare to the randomness. And you guys ask a wonderful question. What is random, right? We have different theoretical randomness, and we need to try that multiple times. Okay, that is a number of permutation. Okay, and then your neighborhood, your global pattern and the local pattern. Okay, two types of measurements, right? Global pattern, you just have a report. And when it identify, oh, it's a cluster pattern, it's meaningful to identify where those clusters are. So that is why we have those global Moran I and local Moran I. okay? Global, you know, GI star, okay? And local GI star, okay? And the difference between local Moran I and local GI star is this one give you outlier. In ACT Pro, it's also called cluster and outlier analysis. But for, you know, GI star, local GI star is called hotspot analysis. That just give you the hotspots and cold spots with high values and low values. Is that good? Is that clear, guys? Well, yeah, okay, good, good. I feel, well, let me share with you. It took me like 2 years, you know, to come up with this clear picture of all these, you know, different methods, okay? But when I finally got it, I feel so satisfied. It's just so satisfying to me. I hope you have the same feeling tonight, but don't worry if you don't, because it took Jane 2 years. She just shared with you her learning process. Okay, feel free to ask me questions, okay, after our class. Otherwise, on Thursday, let me use GODA to demonstrate everything we learned in this lecture based on location, hotspot, okay, the clusters, and based on attributes, the clusters, and the global pattern analysis. The reason I use GODA because it's way easier than QGIS. QGIS, you need to install a package, add in, it's called not extension. It's called, yeah, extension, add in, okay? But that one doesn't work. I tried multiple times. It's just, you know, too many troubles there. So let's use GODA. It's also open source. Okay, so on Thursday, let me demonstrate how to use GODA to do everything here. Okay, I hope you can come back on Thursday to learn another software. Okay, all right, with that, that's it for today. I hope you find it helpful and wish you a great evening. Okay, I will see you on Thursday. Bye, guys.
Bye.
Thank you.
Good night.
Oh, thank you, James, for sharing your map.
Oh, you're welcome. You're welcome.